Finite distributed lags models involves lagged terms of independent variables. On this slide, I used just one independent variable for simplicity, that is just x. In practice, of course, you usually will have more than one independent variables like x1, x2, x3, z1, z2, etc. So those are just extension of the model that we see on the slide. So for the moment, for simplicity, let's stick to one independent variable only. With just one independent variable x, now we are looking at a total of q lags in this model. So we have a q time periods. We would like the model changes in y have changes in y's impact on changes in x impact on y over a period of time, and that period of time is q. We can use this model for two purposes. One is to forecasting. As long as we know the value of x in the last q period, it's possible for us to estimate or forecast what the value of y is in period t plus 1. Second, we can also conduct policy analysis. So for example, if we want to answer this question, what is the effect of a change in x on y? We will look at the marginal effect of corresponding terms. So for example, if we would like to consider the effect as periods way, we can check the coefficient estimate or calculate the marginal effect of x by using any one of those equations, and that's simply just beta s. In this case, that's if it is one period apart, that's beta 1. With this model, essentially, we allow the effect of one unit change in xt to be distributed over the current and the next q periods. So this is why we use xt, xt minus 1, all the way to xt minus q to capture its distributed effect. So those are captured by those betas. And it is called a finite distributed lag model of order q because it stopped at a certain time. So q is not infinite. It could be 5, could be 6, could be 10. Usually it's determined empirically. Okay. Basically assume that after a finite number of periods q, the changes in y no longer have an impact on changes in x no longer have an impact on y, which usually is true in practice. On that note, the coefficients beta is called a distributed lag weight or an s-period delayed multiplier. So multiplier is a term that we need to introduce in this module. It's similar to the way we say coefficient estimate in linear regression analysis. However, because it happens every single period within the q periods, it multiplies on itself. That's why we give it a new name. It's called multiplier. The coefficient of beta now, or when s equals 1, the current period, is called impact multiplier, capture the instant impact from x. So here are some new terms that we also need to introduce when estimating a finite distributed lags model. The immediate impact will be beta naught. However, that's not everything because the effect actually is distributed over a period of time. So the total effect in period t plus 1 will be beta naught plus beta 1. So that's from the current period, and that's from the last period. And when we step into period 2, period t plus 1, the total effect from x will be beta naught, beta 1, and beta 2, and so on. So those quantities are called intertrim multipliers. So anything before the end of this the q period, before the effect of x actually disappear. As a result, the total multiplier is the final effect on y of the sustained increase after q or more periods have elapsed, which means if we add up all those betas from the current period and all of those lagged periods, we have the total effect. We call it total multiplier. Now let's use an example to illustrate how to estimate a finite distributed lags model. The example that we're using now is the Occam's law. It basically models the relationship between unemployment rate and GDP growth. So the relationship is specified as in this model. On the left-hand side, that's our dependent variable. That's the one period change in unemployment rate. Right-hand side is the deviation of GDP growth from a natural growth rate. By natural growth rate, that means this is our expectation. If everything is under control, nothing is disrupting the system, the economy, you will have a natural growth rate. So the system is healthy. So suppose maybe it's 2% or 3%, it's a constant, okay? But we need to estimate it. We can write this as this equation. Essentially, we let DUT to be the difference between those two terms. That's the difference, first order difference of unemployment rate. Right-hand side, as we mentioned before, we don't know the value of GM, but we can have a reasonable estimation, like the simple average of GDP growth rate in the last 30 years. So that will basically average out any up and down disruptions and give us a reasonable estimation of the natural growth rate. So that's natural GDP growth rate is a constant. Gamma here is also a constant, just to be estimated. So if we put those two together like this, and we have an alpha here, that's our constant to be estimated. And the product between gamma and GT is this term. So that's a simple regression model between unemployment rate and the growth of output in the economy. Of course, GT is usually defined in this way. If we would like to introduce the lagged terms of the independent variable, which is GT, into this model, we will have this finite distributed lags model. It stops at period Q. So on this slide, I showed both the line chart and the data of those two variables. Left-hand side, that's DU. You can see the value of DU changes over time. And towards the end of our sampling period, it shoot up significantly, then dropped over there. Similarly, we will see an opposite trend in the second chart, that's GT, and its value frustrated over most of the time, then drop significantly to come back significantly towards the end of the sampling period. One thing I would like to draw attention to is the effect of using lagged variable. So you may notice that in this table, I give you both the current value of UT and GT and lagged value of UT and GT. So UT minus 1 is UT lagged by one term. You may notice that, okay, in the second period, the value actually is the same as the value of UT in the first period. That's the effect of lagging. So we lagged everything by one period. UT minus 1 is one period behind UT. Similarly, GT minus 2 is 2 periods behind GT. By taking the lags of those variables, we will lose observation. So for example, if you lag GT by 2 terms, you will lose the first 2 observations for T equals 1 and T equals 2, because for those 2 periods, we do not have lagged value of GT by 2 periods. Okay, so it depends on how many periods how long the lags are. The longer the lags, the more data you're going to lose. So this is something we really have to bear in mind when modeling data with lag terms. And on this slide, those are the regression outputs for 2 finite distributed lag models. The first one, the lag length is 3, so we lose 3 observations. This is why we have 95 as the number of observation. And the coefficient estimate are given here, and we also have a p-values. You may notice that the last lag term is not significant. R-square is reasonable, okay? And based on this regression output, we can remove GT minus 3 because it's not significant. So after removing GT minus 3, we have this regression model, new regression model. and its lag length is q equals 2 instead of 3. And you may notice that all independent variables are significant at the 5% level, and R square actually didn't drop because I use just R square here. Okay, so that's the output of a finite distributed lags models using this example. And later on, we are going to have a practical sections, and I will demonstrate how to generate those outputs by using stata.